Today's topic is modeling of sponge measures. The first speaker is Christopher Wittmann. He is a PhD candidate at Deltares and Wageningen University. And he's doing his research on the integrated assessment of nature-based solutions to enhance climate resilience. He will present some findings on the suitability of different modeling approaches based on specific criteria. And he'll also show us a glimpse of a simple tool he developed to help selecting a suitable model to quantify sponge measures. The second speaker is Andreja Kopac. She is a hydrologist working in the hydrological analysis and modeling department at the Slovenian Environment Agency. She is currently involved in the SpongeScapes projects and focusing on the implementation of W flow model. And the third speaker will be Dr. Mikołaj Piniewski. He is a professor at the Warsaw University of Life Sciences, head of Department of Hydrology, Meteorology, and Water Management. In SpongeScapes, he coordinates a task related to quantifying the effectiveness of sponge measures under current and future climate. So I think we should start with the first speaker. So Christopher, please, the floor is yours.
Yes, thank you so much, Tamara, for the introduction. As Shirley mentioned, I will be talking today about how to select the appropriate model. So let me just switch this up. And basically, how to select a suitable model for measuring or for quantifying sponge measures. But before I start, I want to give us a short recap on some of the things that we talked about in the previous webinars, and just kind of to give a general overview of what the series has been talking about. So sponge measures, when we talk about sponge measures, we talk about actions that preserve, enhance, or restore water retention, the water retention capacity of a landscape, for example, by intercepting rainfall, by slowing the flow, and storing and slowly releasing that water again. And these individual measures, which are usually on a more local scale, can be scaled up and replicated throughout the landscape to form what we call sponge landscapes to mitigate the effects of floods and droughts, but at the same time also provide some co-benefits such as biodiversity, water quality improvements, and so on. But with respect to the measures themselves, a lot of the effects are still kind of unknown. So we still have a lot of knowledge gaps on how they function and how they interact. And that's why the second webinar, we talked a lot about monitoring and how to monitor and what to take into account when doing that. And this is very important to understand the impact of these measures. But the next question or the next step would be to say, well, what if we want to quantify before you actually implement? And that's where modeling comes into play. So today I will be focusing on models, more importantly, the selection of models. And I'll start by quickly running through, why is it important to select a suitable model, and run you through a little bit, what makes a model suitable for a specific case study. And then if there's some time left, I'll show a short demonstration of the tool that we developed and conclude with some take-home messages. So why is it important to model? So imagine if you want to quantify the effects of certain measures against flash floods. There are certain things that you want to know. For example, you want to know more of the processes of, let's say, the river, so the surface water system. And you want to know how much water there is, you want to know where the water goes, and you want to know how fast it gets there. So already by this very basic example, you know that you need a model that captures all of these different effects that you want to know. So it's a very fast and it's all on the surface. If you look at droughts, for example, it's a slightly different topic. So here on the right, you see a dry water channel. And this is not only basically the last step of the drought, because the effects, they are much more slower, and they occur on a much longer term, and they occur where you don't see it. So in the soil, for example, and in the groundwater before it reaches actually the effects reach the river system. So you need to understand more long-term processes and more processes in the subsurface. So just by these simple examples, we can already see that different processes require different models to capture all of the effects. And that's why the first reason why it's important to select a suitable model is because you have different models that have different specializations. So there is no perfect model that can capture all of the processes in the same manner. So usually we divide it between, let's say, four main types, depending on what type of system they capture. So hydrodynamic models, for example, you would capture more surface water processes, unsaturated zone models, more soil processes, and the groundwater model, more of the groundwater processes. And then you have these more hydrological models that kind of are in between. They capture some processes of all of these, but usually in a much more simplified form. So they're much more useful on, let's say, larger scales. We also have an additional category, which is more statistical and empirical models. These are not really used that much in nature-based solutions and sponge measures, but they can be very important in some special cases, which I will also come to later on. So how do we go about model suitability? In our project, we talk a lot about this, but we wanted to kind of create an understandable way forward of how to select the model. So we started off with a very simple mapping exercise as an online workshop between the model experts within SpongeScapes, within our project, just to start identifying the important factors, what to take into account, and from there start collecting all of these different questions. And then the next step, we wanted to standardize a little bit more and create some sort of comparability between the different modeling tools that we have. So we developed a questionnaire that we would send out to as well the modeling experts within the SpongeScapes, but also to some selected experts outside of SpongeScapes, just to collect a much wider range of tools. So we collected in total a number of 21 tools, and based on these questionnaires and the response, where basically the respondents rated or answered some questions about the suitability in certain environments, we developed this guide for selecting models, where we formulated or identified basically 8 basic criteria that are necessary to assess the suitability. And based on the questionnaire, also we assigned some ratings for each of these criteria for each model. And coming to these criteria, as I said, there are eight different criteria. When we talk about one of the most important ones is scale and the objective. So when I talk about scale, I mean, is it on the flood, more field level? Is it a catchment level, or is it much more like regional basin level? And when we talk about objectives, basically the objective, is it for floods or is it for droughts? And how much level of detail do you need in that system? And you see here that I already started dividing this matrix by model category. So we have, for example, more on the flood side, it's where hydrodynamic models are more suitable, whereas if you're on the drought side, you have groundwater models that are more suitable. And if you're somewhere in between, you kind of want to capture effects from both sides, you would maybe apply more of a hydrological model. But within these different model types, there's also a difference between different types of hydrological models, for example. So if you have a hydrological model and you want to look more kind of to the drought side, maybe it's sufficient to select more of a water balance model. Whereas if you're more interested in more flood aspects, maybe it's preferable to use more of a rainfall runoff model. And the same goes for hydrodynamic models. There are also different kinds. You have more the simplified 1D, one-dimensional models, or the more detailed two-dimensional models. And that's basically a question of scale. First of all, of scale. So if you go to much larger scales, it becomes more efficient, maybe just to focus on more one-dimensional representations of your channel, for example. And the same goes then for the level of detail that you want. If you want, highly detailed effects of your flooding in a floodplain, for example, you would opt maybe more for a 2D approach. If you just want some general effects on water levels, maybe also 1D approach is sufficient. And then conversely, if you look at unsaturated zone models, which are usually much more small scale, if you're on the plot level, you have quite homogeneous system. A 1D approach is perfectly fine. And if you start going to larger scales, then you might want to take a two-dimensional approach. And if you go even larger, then at that point you might want to look into actually using a hydrological model or a groundwater model. Or the next option would be to combine models, so to couple them. Because by coupling models, you can basically extend the range of suitability that these models can go for. So for example, if you have a hydrodynamic model and you couple it with a hydrological model, for example, you can capture a lot more of these more drought-related aspects and soil moisture and so on. And also, if you want a high level of detail for both floods and droughts, then in that case, it makes sense to make a much more, let's say, multiple coupled model where you have groundwater model, a hydrodynamic model, maybe in between a hydrological or soil model as well. So that's just the two criteria or the three criteria. That's scale, objectives, and the level of detail that you want. But there are many more. And for example, how your landscape looks. So the landscape that you have can also define what kind of model might be suitable for your case. Generally, when we talk about topography, so the slope, generally most models are suitable for most environments. So this is maybe not one of the most important, but where it does become important is if you have more extreme cases. So here we have just a kind of like a representation of the landscape from the very high, let's say high mountainous areas up to maybe the more flatter delta areas. So it's just a representation of that kind of continuum. And if you go more to the flat areas, so it's basically areas where you have virtually no slope, then you have, if you want to use a hydrological rainfall runoff model, oftentimes these are not suitable for these very flat areas because they require some sort of slope in order for the equations to function well. So in these cases, you might opt for more hydrodynamic models or groundwater models that can capture a lot more processes. On the other hand, if you go to the other extreme, if you have areas of very high slope, these complex models that incorporate a lot of processes, they can kind of over-calculate some of the effects, even though slope is the most dominant factor. And in that case, you might opt more for these hydrological rainfall runoff models that have more simplified equations. And similarly, if you look at the other geographic conditions, so for example, the geology and specifically the karstic geology. So you have karstic systems. There, these systems can be very complex. So, essentially you would think, okay, well, if you have a complex system, maybe you need a complex model. But in these cases, the geology can be so complex that it might not be easy to represent actually with these and understand all of the different processes. So it might make sense actually to opt maybe more for an empirical model where you make observations of how the water system reacts based on rainfall, rather than trying to understand all of the different processes that are involved. Similarly, if you have a system that's highly managed and highly modified, with a lot of adjustable weirs and so on, you need some sort of model that can capture these processes. I know there are some hydrodynamic models that have them, but also not all of them. So you have to be quite careful of which model is actually suitable for that. And one of the most important criteria, I would say, but also one of the most overlooked, is the measures. generally you can say, well, based on where the measures are implemented, you can already tell, which model would be more suitable. If you're working on something more industry, there may be a dynamic model that captures the channel is good enough, or if you're in more the catchment setting, a groundwater or hydrological model could be a right fit. But this is only for very specific, types of models. And in general, if you have morphological changes, so you make interventions and like a pond, for example, then these classifications might be sufficient. But once we go maybe to other types of measures, you would say maybe land use changes. For example, if you look at land use changes in the in-stream, so maybe like riparian vegetation, you would say, okay, yes, hydrodynamic models are more suitable for these measures, but there are some hydrodynamic models that are better than others at capturing, for example, vegetation or tree trunks or these kinds of things. So these are factors that are very important to take into account. And the same goes for land management. So, for example, if you have on the catchment level a hydrological model and you want to capture the effects of, changing your cropping system or any kind of land management, some hydrological models will be more suitable for capturing these effects than others, and because they have specific functionalities to do so, while others might not. And then the same goes for, let's say, more engineered measures. As I said, the adjustable weirs is one example, but also when we talk about groundwater abstractions or sewer systems and so on. So in the end, the suitability in the case of measures is very tool specific. It's not anymore about the categories, but it's more about actually the specific tool. So we need to capture kind of all of these different effects and the specialization of these tools. And then one of the last ones is if you want to capture something that goes beyond just the hydrological effects, so you want to maybe quantify also other effects that are based on your hydrological models, like erosion, crops, biodiversity, water quality. There are also some models that are more capable than others to include these processes or provide the input in order to model them with others. So, for example, usually for erosion and sediment transport, you might say, well, hydrodynamic models could be a little bit better for that. But it also really depends on the type of hydrodynamic model that you have. Some have these additional functionalities and others don't. So it's really a case-by-case basis. So as before, it's really tool specific and depends on the individual model that you have. And then finally, there are some additional considerations that we really need to take into account. And these are whether it's free or open source, what kind of support they have, what kind of documentation, is it easy to use, is it easy to understand, and how many parameters you use. Is it flexible? Is it applicable also in more data scarce areas, for example? So these are all very important considerations as well. And given time, I think maybe I can give a very quick overview, but of the tool that we developed. And let me just see. Basically, this is a very, very simple Excel tool that I now pre-prepared some answers. And for each of these criteria that I mentioned, there's basically set up like a questionnaire where you just go through the answers. And there's a multiple choice that you can go through for each step. So in this case, I decided to say, well, I want flood and drought quantification on a landscape scale, so medium catchment size. For a rapid assessment, there are no complex systems like based on the geography or the topography. I want in-stream morphological changes, so maybe like a leaky dam, some land use changes in the wider catchment, maybe reforestation, and no kind of additional quantification or something. And you see here that we have mainly hydrological models and hydrological models coupled with hydrodynamic models that are most suitable. And if you, for example, if you want to say, well, maybe I don't want more rapid assessments, something possibly more detailed, you see that, you get a much more complex coupled models that include maybe hydrodynamic and hydrological models. So maybe that's just a quick excursion. Coming back to the presentation, take-home messages. First of all, as you saw before, the model suitability depends on a very wide range of criteria. We tried to condense it to 8 different ones. And it's important to note that no model can do everything. So really picking the right model is really about prioritizing these different criteria and which one is most important to you. It's also important to realize that all models are wrong, and none of them will really capture all of the effects that you want. So it really depends on what the aim of your study is and which of these models are useful to answer your questions. And some other things to keep in mind is that, the modeling only starts with tool selection, but, it still applies to, you still need to, apply good modeling practice for them to be suitable for your area. And then there are also other considerations, such as even if it's technically suitable, it might not be applicable in your case. Maybe, stakeholders have other models that they want to use, or, they use data that maybe doesn't apply to your model. And that leads me to the final point, is that trust beats accuracy with respect to modeling. That when you're deciding which model to use, it's more important that the stakeholders trust the information that's going in and out, rather than having the most accurate model. Sometimes there's an overlap, but generally it's important to take these things into account. And with that, I give back to you, Tamara, and thank you for your attention.
Great. Thank you, Christopher, for your very nice presentation. Before we go to the second speaker, I would just like to say for all of those who joined later, please feel free to write your questions in chat with the speaker you would like to ask them, and they will all be answered after the end of the presentations. And with that, I think we can go to the second speaker. Andrea, please.
Andrea, please unmute.
Sorry. So hello, good morning to everybody. As Tamara said already in the beginning, I will present the modeling of floods and droughts. I'd like to tell you that I joined ARSO 1.5 years ago, so this is my first presentation on hydrological modeling, so please be tolerant. I'll try my best. Okay. Oh, sorry. This is the beginning. Do you see my presentation?
Yes.
Yes? Okay, great. So let's go quickly through the content. We'll start with water cycle and continue with hydrological modeling. I'd like to present WFlow model, which we implemented for our pilot catchment, Gradaščica River. And then I would like to introduce the main model phases or components. The first one being selection of relevant hydrometeorological events. And then almost everything about model setup, followed by calibration and validation, and at the end, model simulation. So starting with water cycle modeling, this is an image that you're probably all familiar with. It describes the water cycle, and it's a good basis to understand the water balance equation, which says that precipitation equals evapotranspiration plus runoff plus delta storage, which is a change in water that is stored in soil or groundwater or surface water. So now that we covered the basics, maybe someone would ask, why do we want to model water cycle? Well, there are at least 4 reasons. We would like to understand how much water is available. We would like to predict extreme weather events such as floods and droughts. we would like to manage water resources sustainably, and we would like to understand the impact of human activities and climate change. But within SpongeScapes project, the main goal is using the model to evaluate the efficiency of sponge measure. So if we continue with model types, Christopher already explained the model types. I would just like to emphasize the three main model types. These are hydrological, hydrodynamic, and groundwater models. We decided to implement WFlow, which is hydrological model, and it has several configurations. For our purpose, the most appropriate was soil bucket model, which is spatially distributed. That means that each cell has its own state, for example, moisture runoff and so on. It's quite a simple concept. So water enters, leaves, and is stored. You can see a scheme of WFlow on your right. Now, if we go more into detail, WFlow goes hand in hand with HydroMT. This is actually a tool that prepares and pre-processes the data, our input data. Output of HydroMT are two files that serve as input for WFlow model, which main output is, of course, river discharge. Now the modeling process, as already mentioned, we always start with selection of relevant hydrometeorological events. Then we have to set up the model. Then this is followed by joy of calibration and validation. And at the end, we perform some simulations to evaluate our sponge measures. About the hydrometeorological events, at the beginning of the SpongeScapes project, flood event categories were defined. You can read the description here. I wouldn't go into detail, but we have identified one extraordinary event that occurred in July 2023, and then one extreme flood that was at the end of October 2014. It has quite strong consequences, flooded main roads and also residentials and commercial buildings. You can see the Gradaščica River a few days after this flood event. On the graph, there is a 2 weeks period, so the last 2 weeks of October, and the peak on 22nd of October is clearly visible. And then besides this extraordinary and extreme event, we also have two other categories. One is ordinary, but this one has almost no impact, so there is no sense to define or to test any sponge measures. But on the other hand, we have also exceptional event, and this one has very severe impact, which can be managed only by early warning and evacuation. So actually there is not possible to find measure that would catch such a exceptional event. The situation is quite similar when talking about droughts. We had one extraordinary event on Gradaščica in 2012, and then extreme event in 2022, when the value of stream flow drought index was significantly below 0 for 8 months. You can see almost dry riverbed of our Gradaščica. And one of the indirect consequences was also the fish mortality due to less oxygen in warm water, along with very likely water pollution. And the graph here represents a longer time period, of course, from even more than January to August, just to see the pattern. And here I have to emphasize the difference between modeling the flood and modeling the drought. So if we go back to this slide, we can consider flood more like a one-off event. So we don't need a very long observation period. We pay attention to the peak and shape of our hydrogram. We are also interested in time of peak and how is the hydrogram decreasing. On the other hand, for the drought, we cannot say that drought is an event because usually it lasts for a long time. So it's more like time continuous state in the nature. So we continue with model setup. This is, by our experience, the most extensive phase. At first, we had to prepare and pre-process the data. We had to take several decisions. They were about the resolution, about observation period. So although we modeled this 2 weeks event in October 2014, we needed longer period to provide the warm state of the model, and we decided for the 2012 to 2014 period. We have chosen hourly time step, and the modeling of sub-catchments is under question right now. Our input data were a digital elevation model, a river network, several meteorological variables, and then land cover, soil map, and so on. As already mentioned, HydroMT creates 2 files. One is static maps, and it's time independent. It contains around 90 parameters. And the other one is forcing file, where we can find hourly data on precipitation, temperature, and potential evapotranspiration. So obviously the main output of WFlow is river discharge. And when we get the model discharges, we have to compare them with observed discharges. And of course, we would like the model to fit the data, observed data well. So we can check this by comparing the discharge curves. And if they are aligned, we can finish the modeling process and live happily ever after. But usually this is not the case. This is not the case. You can see below. The blue curve represents the observed discharges, and the red one is modeled. And obviously they are not aligned. So if the situation is like this, then it's calibration time. The goal of calibration is very clear. We would like to obtain model discharges that are as close as possible to observed discharge values. By that, we have to consider the calibration period. It should be longer because it includes various hydrological conditions. In WFlow calibration method, we set different values of selected parameters, such as vertical or horizontal saturated conductivity, snow parameters, and some others. We have 3 options for setting parameter values. The first one is most simple. We just assign uniform value to a selected parameter. The second one, assign different values to a parameter per subcatchments. And the last one changes the values that are related to other spatial units, such as land cover or soil map, and this is done automatically. And after we have calibrated our model, we would like to check how successful are our calibrated results. For that, we use 2 methods. The first one is very simple. We just visualize the observed values and the model values, and we see how good we capture the peaks and the base flow. So again, as explained before already, when modeling floods, we are more interested in peaks, the intensity of the peak time, and so on. But when modeling droughts, we have to focus more on the base flow. And then the second method for assessing whether the calibration results are successful is quantification of model performance. In hydrology, the most common metrics are Nash-Sutcliffe efficiency, then the normalized version of these metrics, Klein-Gupta efficiency, and root mean squared error. These are the results of our first calibration. On the graph, you can see with blue, we have observed discharges. Red is for baseline model. So this is in the first line. And then the second line is calibration. Blue again observed and gray calibrated. On the right side, you can see cumulative river discharge that represent water balance. And at the bottom, you can see values of Nash-Sutcliffe. And although the value of the calibrated model is better than of the baseline model, it is quite obvious that there is still some room for improvement. So to continue with model validation, now in this phase, we want to validate the model, and the logic is very similar to model calibration. The only difference, but this one is very important, it's the data. Namely, we cannot use the data that were used during calibration, but they should be independent. Everything else is almost the same. So we are now approaching the end. The model simulation. The main idea is to identify sponge measures that we translate into key model parameters with which we can simulate these sponge measures, of course. And then at the end, we want to evaluate the simulation results. SpongeScapes team has defined several technical indicators that help us with this task. And I would just like to say some words about our plan for model simulations. We will focus on land cover scenarios. Since our catchment is very forested, we have almost 70% of forest. We will test the impact of different share types and location of forest in the catchment. So we will either replace forest with some other land cover, for example, grassland or a compacted area, or we will just change the type of forest that we have in the catchment. And of course, then we will assess the results of this using technical indicators that I mentioned before. So this is the end of my presentation. Thank you for your attention and enjoy the third presentation given by Mikołaj.
Great, Andrea, thank you. You had a really nice presentation, so it shouldn't be the last. Thank you very much. And now we're going to our last presenter, Mikołaj. You can share your screen and please.
Good morning, everyone. Let me start straight away. As you already know, we use models for different reasons. And one of these is to answer what-if type of questions. And one of the most commonly asked questions is about climate change, impact on water resources. Climate change is happening now and is expected to continue over the next decades. There is a vast amount of evidence showing how it affects the water cycle at various scales. One of the key symptoms is increased severity and intensity of droughts. And floods. Although devastating floods and severe droughts have happened for centuries, modern attribution studies clearly demonstrate that their likelihood and intensity have increased and can be attributed to climate change. And this challenges the fundamental assumption of stationarity that has historically facilitated management of water supplies and risks. And in this context, two key questions that should be answered are about impacts and resilience. So the first one what effects will climate change have on water resources in terms of quantity and quality? And the second, resilience, will the existing and planned measures, it can ranging from technical infrastructure to NBS and sponge measures like the ones we deal in the project, effectively offset the effects of projected climate change. The recently published SpongeScapes report critically reviewed the evidence of sponge functioning in European landscapes. And one of the key knowledge gaps identified was that measures are often not evaluated against a range of extreme weather events under current and future conditions. And in this regard, the report issued a recommendation that quantifying the impact of measures should take place for a wide range of events and scenarios. Although it may seem that the surge in studies quantifying hydrological response to climate change is a recent phenomenon, it's a misconception. The first studies of this kind were published already in 1980, and back then, future hydrology was derived directly from a global climate model, GCM. And it took nearly 2 decades until first studies similar to those we know today were published. For example, using conceptual hydrological models at a catchment scale, where GCM output was used as a forcing to these models. As of today, workflows for assessing the climate change effect on hydrology are well established. And typical modeling always starts with the global climate models that are forced with greenhouse gas emission scenarios. Then these climate model outputs are transformed using various approaches, such as dynamical downscaling or statistical downscaling. And these pre-processed inputs are then used as forcing to hydrological models, those that were already introduced in the previous talks. The final stage of this workflow is the impact assessment, risk analysis, and these kind of things. The spatial resolution of GCMs ranges between 1 and 200 typically, so it is too coarse for most of hydrological applications at the catchment scale. And this is why downscaling comes into play. And the first approach that I already mentioned, called dynamical downscaling, it's basically the use of a similar kind of model called regional climate model, but for a smaller area, usually a continental scale. And the GCM output is used as boundary condition for these types of models. The second family of approaches, called empirical statistical downscaling, create statistical relationships between GCM outputs and the local weather station data. And the special attention should be paid to bias adjustment methods that actually do not change the spatial scale, but they increase the statistical realism by utilizing relationships between GCM outputs and observations. In practice, hydrologists typically use state-of-the-art climate change datasets, such as the ones listed here. They differ in terms of temporal and spatial resolution, the generation of driving climate models, greenhouse gas emission scenarios, and bias adjustment methods. It should be noted that climate projections at subdaily resolution are rare. So users of some types of models, such as event-based flood models, usually have to use some kind of approaches such as disaggregation based on daily projections in order to produce the forcing for their models. And the second comment is that there are various bias-adjusted Cordex-based climate products available for most of European countries, and very likely they are more accurate than the global or continental products listed here. Okay, this flowchart illustrates a modeling workflow that can be used to answer multiple questions. And let me guide you through these example questions. The first two are quite straightforward and most commonly studied. What is the effect of climate change? This is done basically by comparing the future climate simulation with the baseline climate simulation. So this is how we quantify the effect. The second question, how effective are the measures for the current climate? And then comes the stage in which we combine a future climate with measure parameterization. And with this, we can answer two types of questions. First one is, how effective will the measures be under climate change? And the second one is, what will the combined effect of climate change and the measures be? So it's more about resilience of measures. And this slide shows an example scenario matrix for a combined impact assessment. So the number of scenario combinations can easily run into hundreds, which requires great patience of the modeler, possibly a lot of coffee, and also potentially massive data storage for simulation outputs. So I just want to mention about these practical aspects. In the SpongeScapes project, we have gone halfway towards quantifying the impacts of climate change on water resources and on the measure effectiveness. So I am unable to present the results yet, but another EU project has its results available, and I will use them now as a short, brief case study demonstration. So this case study is a Polish agricultural catchment in which we simulated 5 different measures that we called NSWRM, natural small water retention measures, that resemble very much the sponge measures we investigate in the SpongeScapes project. And one example map shows the afforestation scenario, basically the locations of where the cropland was converted into forests. For the climate change scenarios, we used bias-adjusted Eurocordex simulations, and the full ensemble consisted of 18 simulations. This is quite a lot, so to limit the computational burden, we selected 3 contrasting scenarios that we called cool and dry, cool and wet, and warm and wet. As you will recall, one of my previous slides show an example workflow and the 4 types of questions that can be answered using this workflow. So this example will now serve as a demonstration for this workflow. And I'm using the annual maximum flow indicator. And let's focus on the warm and wet scenario shown in this slide. So the red arrow I displayed now shows the pure climate change effect on annual maximum flow. The second arrow illustrates the effect of measures in the current climate. The third arrow shows the effect of measures under future climates. And finally, the fourth arrow compares the future simulation, future conditions with measures to the baseline conditions. So the interpretation in this case is not very positive because the negative effect of climate change exceeds the positive effect of measures. There are similar examples for other indicators. As you can imagine, annual minimum flows, soil moisture droughts, total nitrogen loads, but I'm not gonna discuss them now. It's just to show you flexibility of this approach. No discussion of climate change modeling can ignore the topic of uncertainty. And I'm pretty sure you've already realized that that this modeling chain includes so many factors and decision points that the total number of combinations of single scenarios can reach several digits. And this modeling chain, so this is what we call the uncertainty cascade. And I'm not aware of any study that actually quantified all different sources of uncertainty across this cascade. However, what is important is to at least make an attempt to reduce uncertainties. And as this image suggests, it can be achieved by different ways. For example, by selecting the most likely scenarios, by using the most reliable methods for certain points in this flow, and the most optimal model structures. So in a recap, everything is in place for methodologies, tools, and data to conduct model-based climate change impact assessment on water resources. And I hope in my talk I managed to guide you through this labyrinth at least a little bit. A practical hint is that you shouldn't underestimate the time and data storage requirements, possibly also hardware requirements for some of the more demanding modeling workflows. And I should also mention that some types of models, such as groundwater models or event-based flood models, may require slightly different approaches than those I presented today. And well, basically there was not enough time to cover everything. And with this, I would like to thank you very much.
Okay, great. Thank you very much for your presentation. Then we have some questions in chat. We are also very close to our allocated time slot, so we'll go to these questions quickly. So we have one question for Andreja. Question is from Masha. As mentioned previously, each model has its own strengths and weaknesses, and it is tailored to a specific research goal. So the question here is, what is the main difference between these models, so WFlow, and another hydrological model, let's say SWOT? So it actually might be considered as a question for both of you, Andrea and Mikołaj.
Well, if I may start, my answer won't be very long because I don't know many other models, especially not SWOT model. Maybe my colleagues can explain something, but otherwise we'll try to find an answer and write it when you will gather all the answers.
So there is, it's hard to provide a brief answer to this question. So maybe we'll use the opportunity to provide a written answer. But in very short, SWOT is a quite complex model, and it's one of its advantages is that it can actually represent various types of measures, maybe not in a very detailed way. So there are specific models that can be better in certain respects, but if your goal is to include very different types of measures ranging from structural to land management and so on in one modeling workflow, and also if you want to include water quality, then it might be a good solution.
Great, thank you. I would just like to remind everyone, so the questions that we don't get to answer now, we will answer them and publish it along with the recording of the webinar. So we can go to more short questions. So maybe Mikołaj, as you were already answering, how do you consider reservoirs in SWOT Plus?
Reservoirs in SWOT Plus can be represented in a similar way as in SWOT. So there is a special, let's say, feature or function that allows for representing them. But there is one advantage coming with this model, and this is decision tables. So we can represent the reservoir outflow rules by decision tables, which can really enhance the simulation of reservoir effects on hydrology.
And would you consider it suitable for nitrogen fluxes?
Well, especially in the context of agricultural landscapes, yes, because I think one of the main strengths of SWOT is the land management and representation of different agricultural practices. So if you want to consider different land use scenarios, changing land management, tillage, and so on, and looking at nitrogen. For sure, it's also better than phosphorus, in my opinion.
Okay, great, thank you. And yeah, I have some resonance. Okay, and considering that our allocated time has passed, I think we should answer all of the remaining questions in written form. And you will receive it when we send you an email that everything is available on our web page.